Okay, hello everyone, and welcome to today's talk about Elasticsearch and Docker. Actually, I would like to tell you about a few things about both of them, and I'll try not to dance on the stage today, and hopefully you'll get something about those two technologies out of the talk today. So, thank you for the introduction. I'll repeat it a bit about me. I'm a Sematex consultant, engineer, and trainer. Mostly focused on technologies around Lucene, like Elasticsearch and Solr. I'm also a co-founder of SolrPL, where we share knowledge about Solr. I also happen to be a father and a husband, and I also wrote a few books, some good, some not. But anyway, those happened. In the next 30 minutes, I would like you to listen to me and learn about two things. First of all, Docker and how you can use it in general and with Elasticsearch. And in addition to that, I'll tell you about a few good practices around Docker and how you run Elasticsearch in that. And of course, about Elasticsearch and how you can tune it to work in the container environment. We already seen how to monitor it, but let's get on what you actually can do with containers. So we are almost all probably familiar with the following thing. We have a development environment where we develop our applications, or developers develop our applications. After they developed, committed, built, and all of that, we go to the test environment when we test the stuff. This is already integrated with some additional components of the application or the whole system. And in general, at least in most cases, those environments differ. Sometimes only slightly, sometimes the difference is very, very large. After that, in most organizations we have the QA environment where we put the already tested stuff fixed, where the QA team can verify that they actually match the expectations of us, of our clients, or the organization as a whole. After that, of course, the productions come in, and again, we have another environment which tend to be different, tend to have more powerful machines that is expected to handle all of the client load we have. And the problems that come with that is that all of our resources are usually not utilized. Of course, we can't make the development environment utilized, but it would be nice to have at least QA and production used as much as we can. Because if we don't, we lose money. That's the common problem. If our production servers run with 30% of CPU, that's something that you usually don't want to go, because if you run it on cloud, then you pay for the whole VM. If you run it on bare metal, then the problem is that you actually over-provision servers, and you lose money again because you had to bought the servers. And the solution to that is that it would be nice to have that all gathered as a single environment and be able to run some kind of software that would allow us to utilize the hardware better. Of course, we have virtual machines, but they come with a certain overhead that I'll show you about. And one more thing that's about all those environments is that they are not equal. Sometimes they are, but in most cases, the small differences that come into play about all those environments make the DevOps people crazy about it. Imagine that the versions is not the same, Java or anything like that, the libraries are not installed, and everything like that comes with the applications, and that can cause problems. We commonly see in the client's environments. As a consultant, I work with them, and we see that people have problems when migrating, deploying to QA, deploying to production, and see that something is not working. Why? Because the environments are not the same. And the solution to that is actually packaging our software in a container that comes with the runtime environment, all the libraries that we need, and just put it on all those environments. The same container that was already developed and tested, and we can just deploy it on production and be sure that this is the same thing that we actually tested, the same thing that we worked with, and we have the same libraries and all of that. And The solution to that is, of course, using containers. The thing is that today I'll talk about Docker and Elasticsearch with it, but the Docker is not the only solution out there. Some of the examples are Kubernetes from Google. Amazon has their own environment for running containers. We have multiple providers that can run containers. We have ELK, Spoonnet that can help us with all those problems that we have. In general, with containers, with not equal environments, with resource utilization and server over provisioning. So what is Docker? We can say that this is a pretty straightforward piece of software that packages our applications with all the runtime environment and all the libraries that we need to run it. So it's lightweight because it doesn't come with all the overhead that virtual machines have. I'll show you what the difference is in just a moment. It's based on open standards. It's running on Linux, so we are mostly all familiar with that. And it's secure. All the pieces of the environment is separated from each other. Of course, to a certain extent, not because there is a still host operating system. So how does it differ from the standard virtual machines that we are used to using? So the traditional virtual machine comes with certain layers. We can visualize it. We have the hardware layer, of course, the bare metal, and then we have the host operating system that runs that. Next, we have the hypervisor. That is the piece of software that controls the virtual machines. And for each of our applications, or each of our virtual machine that is running there, we have the guest operating system. So each virtual machines run its own operating system, have its own overhead. And then we have, of course, the libraries for our applications and the applications themselves. When it comes to containers, we, of course, have those two common pieces, the hardware and the host operating system. But instead of the hypervisor, in terms of Docker, we have the Docker engine, a piece of software that can run the containers. It runs, currently it runs on Linux, as the kernel supports all the needed features. Of course, it runs on Microsoft Windows, if you would like, and with certain virtual machine, in addition to that, it runs on OS X as well. So, but what is great about containers is that they don't have the overhead of the guest operating system. As you can see on the slide, here on the top of the Docker engine, we have already the applications and the libraries themselves. The container is pretty lightweight, and we can just ignore its presence there. And this is how our containers will work when we put it into Docker. And of course, Docker is not only the Docker engine itself. For example, we have the Docker Swarm, which allows us to connect multiple Docker engines together and work with them like a single one present, installed on different machines, installed on different bare metal machines actually, and have them combined together. And when it comes to the second piece of software I would like to talk about today is Elasticsearch. We choose it for running as a search-based application because of a few things. It was designed with distribution in mind, and it's distributed from the ground to the top. So all the functionalities work in distributed environment. It can synchronize it. Nodes of Elasticsearch can synchronize together without any issues, without us having to worry about that. In addition to that, it's built on Apache Lucene, the most commonly used open source full-text search engine library out there, written in Java without any additional libraries. Very efficient, very small, and very actively developed with a large community around it. It has a reasonable defaults when the Elasticsearch itself, so if you unpack it and just run it, it's already ready for development mode. In production, it needs some tuning, but that's the usual case. It talks to us in JSON, and we talk to it with JSON, so it's pretty human-friendly, not only machine-friendly, but also human, so we can easily understand what the response is without the need of any tools. The curl is more than enough to interact with Elasticsearch. And finally, it's RESTful, like those kittens here, and we can easily memorize its API. Once you get used to it and start using it, it's really become your second nature, calling of the APIs of Elasticsearch. So how to run the official Elasticsearch image on Docker? It's very simple. After you install Docker, you just need to type docker run -d means detach Elasticsearch, and it just runs. The container will, if you don't have the image and the container itself in your environment or your production environment or anywhere else, it will just download the image and start Elasticsearch, and that's all. Everything is running. You don't need to care about anything else. Of course, you can specify that you want the latest. You may specify the version of Elasticsearch. So whatever if it's published on the official repository of the Docker, in so-called Docker Hub, you have that, and it will be downloaded and run. We can also provide some additional names and properties for Docker. It's usually very nice to be able to do that, because you want Elasticsearch to be running on with a certain names, because Elasticsearch by default chooses a random name for its nodes, and that can cause problems, especially when using monitoring, because you want to know especially which node you are talking about even after the node restarts. And you can also use the UI provided with Docker Toolbox to control your containers and choose which one to run and all of that. That's the basics. Of course, you can use the constraints to give a container some piece of your bare metal hardware or your cloud or anything like that. It wouldn't be really useful if you couldn't do that. So for example, you can just run -m and specify the amount of memory the container can use, and till 1.8, I think it was up to 10 gigabytes of memory. Right now it's out, I think, up to 100 or something like that. So we can really use what we want. We can specify things like that. We don't want the memory to be swapped. It's very useful for Elasticsearch because we don't want Elasticsearch memory, the part of memory used by Elasticsearch, to be put into swap. That's killing the performance of Elasticsearch. In addition to that, we can specify which cores of our bare metal machine Elasticsearching container will be able to use. Like here, it will be able to use the ones enumerated as 1 and 3. And of course, we can control the CPU cycles. Like here, if that would be run on a single core, it would be about 25% of the cycles to be used. All the commands for the constraints of Docker are listed in the Docker documentation. So if you're interested in that, it's a very nice piece of text to look at. But Docker also allows us to create our own images. For example, here, if we would like to have in our organization our own image of the container with our own configuration of Elasticsearch already tuned to and prepared for us, we can just use the official image and create a file called Docker file and tell from Elasticsearch, which means from the image, take and add the Elasticsearch YML file and put it into container into that particular USR share Elasticsearch config directory. After we run the Docker build and give it a name, what Docker will do is it will just build the image that we can reuse or publish to our own repository, and all the machines will be able to use it whenever we specify the DevOps/example name, and if we would like to run that particular image. There are a few problems and obstacles when running Docker and Elasticsearch together. First of all is the network. In most cases, you would like to have the network not expose the whole network of Elasticsearch to all your applications, and Docker allows us to do that. In addition to that, you want certain ports of Elasticsearch to be forwarded outside of the container for your applications to be able to connect to it, or your clients like Vue running commands of the administration API. So we can just specify the -p and say which port of Elasticsearch should be forwarded outside to the container, like here the ports 9200 and 9300. So that's simple. We can also tell Elasticsearch to which host it should bind itself. Like here, network publish host, and tell it to bind to that particular IP address and listen on that address. The thing is to remember here is that those commands should work with Elasticsearch and the container for 2.0 the newest version of Elasticsearch. For the older version, you need to prefix it with es dot, so it would be like es.network publish host. We can also, of course, combine all that all together, alter Elasticsearch to bind to all possible hosts that containers actually see. And there are a few good practices I would like to share today when it comes to containers and Elasticsearch, is that you should usually create a separate network for your whole Elasticsearch cluster. It's, as I said, you don't want for all other pieces of software in your application that builds your application to be able to connect to it, interact with it. Usually want only some pieces of Elasticsearch that I will just show you in a second to be able to expose all the ports and interact with the other parts of your software. So create a separate network. Also use common host names for your containers and Elasticsearch because you would like to know where Elasticsearch is actually running. Because if you run hundreds of containers, that having them named randomly and having random host names is not a very good idea, especially when you would like to see what's on the given container, where it should be, where it's running, what's the constraints, and all of that. In addition to that, we should only export and expose the ports to the 9200 and 9300 to only client nodes, and all the other nodes should be pointing to the master nodes only. And I'll tell you why in just a second. In addition to that, the next problem when dealing with containers is that they are mostly stateless. At least to a few versions back, they were mostly stateless, and that means that whenever your container was restarted and destroyed, the data was not persistent. Of course, you don't want your indexed data that was indexed in Elasticsearch to be lost. So we have a few, right now we have a few possibilities of dealing with that. The first possibility is just mapping your local directory, local to the operating system, the host operating system, like here the opt Elasticsearch data, to a directory in a container, and container will use that directory to just store the data there. And if the data is on the host operating system, then there is no problem with persistence. The second thing is to use data-only containers. Those are the stateful containers that are not that old. They are quite young. And the thing to remember is to remember about permissions. Because if containers interact with the local operating system to the host system, then it needs to have the permissions to write and read from that directories. And the data-only volumes in Docker, they are bypassing the union file system of Docker, which means they can interact with the operating system storage. In addition to that, the containers can be shared, the data-only containers can be shared between multiple containers of Elasticsearch. They are very easy to create. So we just run docker create, tell which volumes to mount, give it a name, and then we can use it. Again, we're just using the minus values from and telling which volumes should be used. And Docker engine will do everything else for us. The thing is that volumes that are stateless, which are data-only volumes, are persisted, and you don't need to care about if the container was deleted or not. They will still be persisted on the file system of the host operating system. It doesn't matter if you run it on Swarm or on a single host. There'll still be the data will still be persisted and not lost whenever it comes. Now, what to do to have a highly available Elasticsearch cluster, because this is what we actually want to aim for, right? We don't want Elasticsearch to be breaking, dropping off, and all of that. To allow us to do that, Elasticsearch have a notion of 3 types of nodes. The master nodes, the data-only nodes, and the client nodes. The master nodes are the ones that are responsible for handling the cluster state. We say that some of the nodes should be the masters, and only a single master will be present at the same time, but there will be, for example, like here, 3 nodes that are eligible for the master role. Then we have the data containers, data nodes, that can only store the data in Elasticsearch indices, which means that those nodes will be the ones that hold the actual data of the indices and run the partial queries and the indexation on them. And finally, the client-only nodes, which are the ones that we send data to, send queries to, and they are responsible for forwarding the data to an appropriate shard, and in addition to that, gather the data from all the data nodes and return us with the results for our queries. So that's how it goes. And there are a few things about that architecture of Elasticsearch that you should remember. First of all, you should set the minimum master nodes in your configuration. And it should be set to 50% of your master eligible nodes plus 1. This is done to avoid network splitting, and because Elasticsearch with the default configuration has one problem. Whenever a network split comes, and that will come sooner or later, Elasticsearch will try to build clusters in each of the splitted networks. So if we would split the network like one of the segments would have only one master and 2 data nodes and 1 client, and the other split would have the other part of the network, 2 clusters would be created if we don't have the minimum master node set. And if your indexation continues, then those 2 clusters would get separate parts of data. If then the networks were joined and fixed, then your Elasticsearch cluster would blow up because it wouldn't know which part of data is the one that should be actually taken into consideration, and you would have to do manual work to delete part of the data to actually be able to use the cluster or the indices that the data was put into in that particular case. So my minimum master nodes helps with that, because Elasticsearch knows that if it sees less than 50% plus 1 master eligible nodes, it won't create a new cluster out of that. In addition to that, we have a few properties that allows us to work with Elasticsearch quite more efficiently. Those are recovery after node and recovery expected nodes, which controls the so-called recovery process, which is the process of reading the indices and bringing them to be ready for searching and indexing. We have the allocation node concurrent recoveries, which controls how much I/O and CPU actually Elastic will use when it comes to the recovery process. The more concurrent streams you use, the higher pressure will be put on Elasticsearch and your disks, but the faster the recovery process will be. The node left delay timeout, which is right now by default set to 1 minute, allows us to not have a shard dance, which means that Elasticsearch will wait 1 minute before moving the shards around whenever a cluster loses 1 or more nodes. And finally, if we have some indices that are very important compared to others, we can set the index priority, and that will tell Elasticsearch to start the recovery process of those indices faster compared to the other. And how to run master, client, and data nodes in Docker? It's very simple. We use just the Docker run -d again Elasticsearch, and we tell node master true and node data and node client set to false, and we have a ready container to be working as a master. The same goes with the data nodes. And the same goes with the data and client nodes, where you can see that the appropriate property just needs to be set to true and all the other to false, and that will work. Of course, again, for Elasticsearch, not to O. The older ones, you need to prefix that property with ES dot to be working. This is for the master nodes. A bit of scaling. Imagine those 4 Elasticsearch nodes running in a containers, and what we can do with it, we can create an index, for example, like the Devops index here, that will have 4 shards. So there are 2 types of shards in Elasticsearch that build up indices. The first are the primaries, the ones that take the roles of the ones that are first getting the data, the ones that start the indexation, and then we have the replicas, their physical copies. So the primaries, once we create the index, we can't change that. We only have the possibility of specifying how much primaries an index will have sorry, during the index creation. So if, for example, if you want to utilize your containers and your hardware properly, you should spread the index to multiple shards. So each, for example, each node have its own shard, the primary shard, so the indexation will be parallelized. And then we can create replicas which help us, for example, with the query throughput. And that can be done dynamically on using the API. Like here, we're telling that Elasticsearch have one replica, and just Elasticsearch will just create another shard that is called replica, and it will copy the data between the primaries and the replicas. And Elasticsearch is intelligent enough to not put the primary and the replica shard on the same node. We can also configure it to not put it on the same bare metal machine using cluster allocation. And all other stuff is done automatically. We can create more replicas and have more of them, of course. We can remove them, again, using the API. And Elasticsearch will do that automatically without any cluster on hold or delaying any operations. So that's very nice. And finally, if we remove nodes, what Elasticsearch will do is it will just move the unassigned and the replicas and primaries that were on those nodes to the nodes that are left in the cluster. Of course, if we have enough data, because we need to have primaries to be able to create replicas. Finally, if we will shut down one more node, then the replicas will go into so-called unassigned state, which means that Elasticsearch just can't use them because of, by default, it can't put the primary and replica on the same node because it wouldn't make sense. When a node would go down, you would lose data anyway. When it comes to indexation, there are a few things to remember. So it can help you with throughput and performance. There are a few properties, and 4 of them are, in my opinion, the most commonly tuned up. We have the index buffer size, which tells you how much memory Elasticsearch can use per shard for indexing. We have the minimum buffer size. We have the max index buffer size, which is unbound. By default, we should set it to some amount of memory because the index buffer size is per shard. And imagine if you have 30 shards on your node and 10% of memory can be used for indexing by each shards, then for 30 shards you can use up to 300%. This is 3 times more than you can actually physically have. So out of memory errors will happen, so that maximum indexing buffer size is good to be set. But in general, if you want higher indexing throughput, put more RAM for Elasticsearch to be able to use for indexation. If you want lower indexing throughput because you don't have enough memory, then just lower the values and Elasticsearch will be fine, though the indexation will be slower, slightly. What if you have time-based data? There are a few things, again, a few common practices that you can do. For example, for time-based data, you can use the time-based indices. It doesn't matter if it's daily, like here. You can use the hourly if you have enough data that your indices will grow. You can have monthly, weekly indices. Anyway, the trick here is to have aliases in Elasticsearch used together with indices. For example, let's create an index for yesterday. Let's index data to it, and create 2 aliases: the week and today. The today will be used for indexing. The weekly will be used for searching. Those are the assumptions that we usually see. Usually people want to search in about week worth of data but when it comes to logs, for example, but we only index the data that comes in real time. So the aliases, to create aliases is again a simple API call. We just said add and we specify which index should be named how, and we can do that. The thing with aliases, it's not a rocket science. It just helps us to index data without the applications that are indexing to know exactly what the index naming scheme is. So here we only will use 2 names, today and week. The next day we would create another index and update our aliases. So today would be for today's index, and the week would contain two indices, and so on and so forth. Still, we use only 2 names for searching. This is done because Elasticsearch in its internals with the Lucene does something called segment merging. the higher the volume of the data is, the more data you have in your indices, the more segments will be created. So small pieces of, small or larger pieces of actual Lucene index that are merged together to allow for better searching. And the thing is that what merging means is just copying the data to one higher segment in terms of data volume. So you can imagine if you have segments of 10 gigabytes and 10 of them, to create one segment of 100 gigabytes, it just needs to copy those 10 gigabyte segments into one segment, and that means I/O and CPU. And that's a painful process. And that's done in parallel to indexation in Lucene, so that can slow down your indexation greatly. So to keep the data volume under control, you create smaller indices to allow the segments to be smaller and the mergers to be less painful. In addition to that, Elasticsearch allows us to create an architecture called hot-cold, which also helps us to deal with time-based data. The trick here is to set the properties in Elasticsearch, like we would set the first two nodes have a property called node.tag equals hot. Those servers can be, for example, way better in terms of I/O, like have SSDs, have a lot of CPU, have a lot of memory. So we will use them for indexing lots of data, like all the logs we have in our organization, and to search for the most recent data. And the cold nodes, the one tagged with node.tag equals cold, would be used as some kind of archive for the older data, if it's week or month or years, like some organizations needs to hold the data. But the theory around that is that those nodes will be used less because they have an archive. And what Elasticsearch allows us is when we create an index like the data to 2015, 11, 23rd, is we say, hey, Elasticsearch, create it on the hot node. What Elasticsearch is will create it on the hot node. When we index it, only the hot node will be used for indexing. So all the merging, all the writing to I/O will be done on that node. And then when we move to another day, we just say, exclude it from the hot nodes and move it to the cold nodes. That means that Elasticsearch will move this index and all the shards that come with it to the cold archive nodes that can have, for example, spinning disks and be less expensive. It all comes to money, how much data you can put in the same cluster, right? Because, of course, we know we can buy large hardware and just put everything, but that costs. And the same goes with another day, and another day we would just move it with a simple API calls, and all of that would be used. This is a very common practice when it comes to handling logs, and that allows people to actually handle a lot more throughput of data daily than the common architecture that would just take a container with Elasticsearch, put it, and forget about it. So this is something to play with. Again, to use it with Docker, we can have a container that puts less restrictive constraints on the hot nodes, like give it a more memory, give it all CPUs on the bare metal machine that we can have, and the cold nodes would just have more restrictive constraints and run it like this. Of course, time-based data is not all we deal with. When it comes to, for example, multiple tenants and data like this, we can't use those two tricks that I just talked about, time-based indices and hot-cold nodes. What we can use actually is routing, especially for example when the data is user-based. So how does indexation without routing works? When an application sends the data, Elasticsearch uses so-called hashing algorithm to calculate the hash of the document based on its identifier. And then, based on that, it puts it into one of the shards of the indices. And in general, it will round robin around all the shards and just put it more or less evenly in all the shards. But when we have routing, we can use, for example, a username or user ID or anything that identifies user and put it into a single shard. And that allows us to actually utilize the hardware in more efficient way when it comes to the queries for some routes, like for some of the users. Again, when the queries come, what Elasticsearch will do is it will go with two phases, the scatter and gather phase. First, the scatter phase spreads the query to all the shards that are building the index, gathers the IDs of the document, and then the gather phase asks again for the documents that are relevant for the query. And when routing is used, we can only say, hey, we know where the data for that particular user lives in. Just omit the scatter gather phase and go for a single shard and just get the data. The last thing here is we did a test some time ago for one of the clients, and we compared the difference for them when it comes to 200 shards, sorry, they had with one replica. And the problem was that without routing, as a throughput for their queries with faceting back then, and with a normal query, was about 90 queries per minute. That's very, very high. Each query to the 90% line of the queries was about 5 seconds. It's a lot. And when we changed the architecture to use routing for that particular case, you can see that the number of queries per second for 20 threads using JMeter was about 91, a bit more, with the 90% line less than 1 second. So the difference is noticeable without it's enough to see here. So the thing is, the really last thing about all of that is that you should monitor your cluster. Depending on what you want, is either if you are going with the solutions that, for example, we as a Sematex provide, or if you go with another open source solution out there. There are multiple technologies to monitor Elasticsearch and Docker, and you shouldn't go to production without any monitoring, because if you want to fix something, you actually want to know what you would like to fix. And without monitoring, you are just as blind as a child running around the dark room. So you need to know what should be fixed to actually fix it. And that's all for today. Thank you for listening. If you have any questions, I think we don't have time right now, but I'll be here. And I'll answer anything you would like to know about Elasticsearch and Docker. And if you would like to contact me, I'm available at Twitter. This is my mail. This is my company site. And thank you for listening, and enjoy the rest of the conference.